Hi, so let us continue with the solution of the boundary layer equations for surfaces other than a flat plate, right? So we came up to this place where we were using a power law for the velocity description, right? If you see here, so we were using this description, right? And with that, we have come up with a solution. Finally, we stopped where we got a description for delta bar, which is given by this expression in 8, and we said this is a solution for beta not equal to 2, right? And where I stopped was what happens if beta is equal to 2, right? If you've not sort of had time to think about that, let's go and discuss that and then proceed further. Okay, so you can see from the expression here for beta, right? So if you see that, if beta is equal to 2, then of course, so if beta is equal to 2, I think m would become very, very large, right? So, and if that happens, if m would become extremely large, then if you come and look at this equation right here at 8, right, m is very, very large, and this equation is a inverse function of m, right? So delta bar is an inverse function of m, so that means delta bar will, if that happens, so then automatically this would mean that delta bar will tend to 0, right? And if that happens, then this equation doesn't have any meaning again, because all we're trying to do here is to understand the behavior of the boundary layer, and if boundary layer itself is becoming insignificant, then it doesn't mean anything. So we have to restrict our solution to beta is not equal to 2, right? Beta is not equal to 2. Now, but what do we do if if beta is equal to 2? Then we should have a solution for that. So in that case, basically, what we will do is, if you okay, so we have we're going to use this equation 6 here, expression 6 here. So let us see what happens, what we will do in case. Okay, so let us say that for beta equal to 2, okay, so beta is equal to 2, okay, let us say that u infinity by phi, okay, is equal to b exponential 2 p zeta. Okay. Now, if we have an expression like that, okay, then if we can go here, we can go again to this expression at 6, where we basically say that alpha 1 is 1. We took that, so we will keep that. Okay. Now we have got an expression for basically u infinity, and this is un, right? So, and we have the expression given in 6. So using this, so let's just say, okay, so using 6, okay, if we use that, what we get is delta bar, okay, b exponential 2pc, okay, d delta bar dz is equal to 1 minus beta. Okay. Okay, so if I were to sort of, okay, so let me do a couple of steps, and then again, I think slowly you should get a hang of completing these derivations. I will also post this again on the website, so I'll miss a couple of steps, right? Or let me write, so B delta bar d delta bar, okay, is equal to 1 minus beta, okay, exponential minus 2p zeta, okay. I'm just rearranging the terms, okay. Hopefully this is easy for you to understand. Okay, and now what I will do is I will take integral, okay, I will take integral, so I will take the integral this way, okay, taking the constants out. So if I do that, then, so if I take the integral, then what I get is essentially, well, b delta bar square by 2, okay, is equal to 1 minus beta, okay, exponential minus 2p zeta by minus 2p, right? So then, right, I'm going to miss just a step, or I'm going to just say delta bar is equal to beta minus 1 by b into p exponential minus p zeta. Okay, if I do that, but then like we've said, this is for beta is equal to 2, right? So if beta is equal to 2, again, beta is equal to 2, therefore, okay, delta bar is equal to this exponential minus p zeta, right? So you have a different expression for delta bars, and we have to do that, right? So we have to do that, right? Because let's call this as 9. Okay, so we need to do this because otherwise the expression that what we did earlier, okay, when we take the power law, it doesn't work for beta is equal to 2. So we need to have something else for. So this is a special case basically. So we will keep that. Okay, so now let us look at the variable eta and how we're going to treat that, okay? So if we go there, so let us see what we will do in that case. So let us see how we will treat the okay, so what we will do is, this is the similarity variable. Sorry about that. Okay, so similarity variable eta, right? So what we're going to do here now, okay? So now eta, okay, is equal to y by L, okay, under root of RE by delta, right? Where, of course, RE is VL by nu, right? And zeta is equal to x by L. Right, we know that. So then, eta can be written as y by L, okay, under root VL, okay, under root nu, under root, not under root, this is delta bar. What is delta bar? Did we just define that earlier on? Okay. Okay. How have we said what is delta bar? Okay, let us okay, so we have our delta bar as what we do here. So it's basically the stretched version of your boundary layer displacement thickness, right? Not boundary layer thickness, basically. Okay, so if I do that, okay, so then this I can write as y, okay, under root of v under root of L and nu, okay, into under root, okay, so I think, okay, I missed something here, okay, so this here is my delta bar, which I kind of wrote out, okay, so how do I write this? So under root L this, okay, you get that, right? So you have an under root L here in the numerator, and you've got an L here. So I'm kind of dividing by that. So I get, so I put these two inside. So L and nu together. And I'm writing out 1 by delta bar, right? Which is nothing but here. This m value, this one, 8, right? So that is 8, and the way I write that out is, again, b 1 plus m, okay, by 2, okay, into 1 by zeta to the power 1 minus m by 2. Okay, you've got that. So then again, so now I hope that's clear. Okay, so then this is equal to, so again this is, okay, let's write it here. So this is equal to y, and I put all this inside, these two inside, so I get b v 1 plus m, right, then to that 2l nu, okay, into, so I got all these things inside of this, okay, so 1 by zeta to the power half, right, into 1 by zeta to the power minus m by 2. Okay, so if I do that, okay, then this is again equal to y, okay, b v 1 plus m by 2l nu, okay, and this one is under root of zeta, right? So I can write this basically, okay, I can write that as basically, I can write this as under root of zeta, and zeta is x by L. So what I can write is under root of x by L, right, into, I will write to the positive power m by 2. So clearly you can see this L and L will kind of, cancel out, okay. So if I do that, this is equal to y, okay. So 2x nu, okay. So this becomes b v 1 plus m 2x nu and zeta to the power m by 2. Okay, so that's my eta. So I can write my eta in this form, right? So this is nothing but my eta. So right, that's my eta. Now, however, okay, now we will write out the power law. U infinity by v is equal to b zeta to the power m, right? Or b into v, right? Okay, so b into v, if you see, is equal to u infinity zeta to the power m. Is that fine? Right? So I missed a step here. So all I did is take v here, right? I moved the, okay, let me do that step here, okay, to make it just a little bit clear. So basically what I said is u infinity is bv zeta to the power m. So then I bring the zeta to the power m down here, so that left hand side is u infinity by zeta to the power m, which is equal to bv, right? So then I can write it in this fashion. So then that basically is bv, right? And I can write this in this fashion when I took the power to the top. So therefore I get this. So basically what I'm saying is we can replace, the bv term here by u infinity zeta to the power minus m. Right? So if I were to do that, so then we input that in here. We input that in there, okay? Then, so therefore, eta is equal to, okay, y under root, okay, it is equal to, okay, under root, so 1 plus m by 2x nu, okay, bv is u infinity zeta to the power minus m, right? And this is zeta to the power m by 2. Okay, so if I do that, okay, so then, I mean, this makes it simple, hopefully you can see that, right? So we'll take zeta outside, right? So, or eta is y, okay, under root 1 plus m by 2x nu u infinity zeta to the power minus m by 2 zeta to the power m by 2. So these two cancel out, right? These two cancel out, and what I'm left out with, therefore, eta is equal to y 1 plus m by 2x nu u infinity. I hope you see some, similarity or pattern in the eta that we had for a flat plate. Okay, so if I do that, okay, now beta, okay, if I were to introduce beta in here, right, so I got m, so now beta is, see, beta is 2m by m plus 1, right? And 1 plus m, yeah, well, this is just for, writing out purposes, is 2 minus beta, right? Then what happens to my eta? So 1 plus m here, right? 1 plus m here, right here, this, I can write that as 2 by 2 minus beta, okay? Yeah, so basically that, okay? Or 1 plus m by 2, is equal to 1 by 2 minus beta. I think that's better. So 1 plus m by 2, right, is equal to 1 by 2 minus beta. Okay, and that's it basically. So therefore eta is y. Okay, this thing. So it is u infinity, okay, by nu, okay, into 2 minus beta into 1 by x, right? That's it. And here, this is where beta is not equal to 2. So this is for that case. I mean, that's what we were doing so far, right? So then we get an expression for the eta, and let's call that as 10. Right, makes sense? I mean, this is just a lot of math, okay? So now, so therefore, well, so now what do these numbers mean? So when we do things like this, right, it is very interesting that, I mean, we shall be able to get solutions for, various combinations of beta and things like that. It's interesting that they actually boil down to something, physical. It's actually, physically it means some kind of a flow. For example, right, having done this, so in this particular case, right, we were doing alpha 1 is equal to 1, right? So we said positive, negative, and 0. That's what we're going to look at, the behavior of that, right? So now, what happens is, if you were to solve this, okay, if you were to solve this, okay, then m is equal to 0, right, which means that beta is equal to 0, right? If you do that, and if you solve for this, right, what should you get? So because now the only thing is that if for this eta and the corresponding delta bar, right, so whatever you get from here, right, so these things are in terms of beta, right. Let's just remind ourselves. So this is for, beta is equal to 2. So I mean here, so this equation 9 is for beta is equal to 2. Okay, so that is that. Now, so we had a delta star, okay, a delta bar, which is given by 8. You got something like that. So you could write this, 1 plus m by 2 is basically 1 by 1, 2 minus beta, right? So you could write this in terms of beta. So you have a delta bar, which is in terms of beta, right? So, and this is your description, right? It's obeying a power law. Alpha 1 is 1, right? And alpha 2 is equal to alpha 3, and that which is equal to beta, right? So that's where we started. So now m and beta is something which is interesting, and using that we were able to get an expression for delta bar. Now what happens is that if for m is equal to 0 and beta is equal to 0, it actually boils down to, so think about that, think about what this would mean, right? So beta is equal to 0 and m is equal to 0, what does this boil down to? Think about that. Okay, think about that before I write down what that means. And okay, let me write down, if this is the case, right, what happens to our eta? Let me just sort of write that down. If for this particular case, okay, so here eta is equal to y under root u infinity 2 nu x, right? And what is our delta bar? Let us go and see. We have a delta bar, right? Right, so m is also 0. If I have a delta bar, what does that mean? So say for m is equal to 0, delta bar is equal to 2 by b, okay, zeta to the power half. Okay, so now this is what we get for delta bar. Now, if you remember, okay, what we so fine. So you'll have to now figure out what the function, the constant b will be. Now, if you can recall what this eta was looking like, so this basically what is happening here is that this is boiling down to flow past a flat plate at 0 incidence, which we studied at length, right? So essentially what we're saying is that if you took this kind of an expression, right, so for certain values of m and beta, you would be able to get a solution for the flat plate which is lying in parallel to and through the free stream. So basically 0 incidence, which means that this is your flat plate, this is your flat plate, and this is your incoming free stream. So the incidence, so in here is basically 0, right? So if the flat plate instead was like this, okay, so it is making some angle with the direction of free stream, then it would have an incidence. So that's what we mean, call it angle of attack if you will. So this is what you mean. So this is something this is what we started with, and we spent a lot of time trying to understand the flow past a flat plate, right? So essentially for these comments, so numerically m is equal to 0 and beta is equal to 0 boils down to flow past a flat plate at 0 incidence. Okay, and the second case, okay, that m is equal to 1, okay, and beta is equal to 1, okay, what happens to our eta then? Okay, what happens to our eta then? Eta is y under root u infinity. 2 minus 1 is basically 1, so nu x, right? This is your eta, and then the corresponding delta bar, and this is flow close to a stagnation point, right? It is a flow which is close to a stagnation point. Okay, so that's what. Now the thing is, we will move into the other two cases that we said we'll talk about alpha 1 is negative and alpha 1 is positive, alpha 1 is 0. Now, I think this is a good place to stop. Let me just kind of summarize this and say, numerically, so numerically when we're trying to look at a solution, so, these are, values. So, if we assign different values numerically, right, to these, beta and m, right, we will get physically different flows. So, this would be able, so if you use this, right, what was a velocity description? Our velocity description is this power law m, right. So, if you see what this exactly means is that say m is equal to 0, that is the flow past a flat plate, right. If m is equal to 0, right, which means beta is equal to 0, then the power law, from the power law we get this is equal to b, that is all, right, and b is a constant, you can take that as 1 or you can take that as 2, it does not matter. So, if it is for a flat plate, you just have to see what, you can just take b as 1, right. So, if you take that, if you say you take say b is a constant and I take b as 1, then as we wrote down here, right, if b is 1, then zeta, okay. So, what was zeta? Zeta is basically x by L, right. Where did we define zeta? Okay. So, zeta is our x by L. So, right. So, I mean, anyway, you can look at that. Where is our right. So, zeta is x by L, right. So, I can say if zeta, so x by L, right. Now, if I look at this here, right, correct. So, b is 1, so delta bar is basically equal to under root of 2, right, and under root of x by L, okay, or delta bar is basically 2x by L. Okay. So, x by L, now you can put in the description for delta bar and just get something for delta, get the expression for delta. So, the whole thing is that if we can get an expression in this fashion, then we can change the values, numerical values of beta and m, right, and assign different values of m, right, and this gives you the ability to study different physical flows. I think that's a very powerful tool that you have, right. So, if you use a description like this, right, and numerically all you have to do is just change a couple of parameters, and that actually helps you to study different physical flows, right. And think of that in terms of if you didn't have this tool, if you had to study a flat plate and if you had to study a flow near a near say in this particular case we talked about flow near a stagnation point, you would have to build that separately and do that. Here it is all you need to do is change its parameters and go ahead and look at it. So, we will stop here, and in the next module we will go and look at the other couple of cases. Okay, thanks.